Here we go.
Yell at you.
You may yell, you can do it if you want. Okay. All right, so with the fundamental theorem of calculus, which states that the integral from a to b of a derivative function is equal to the original function evaluated at b minus the original function evaluated at a. And this represents the change in the height of the original function between a and b. Okay, in order to give you a graphic representation of the fundamental theorem of calculus, I'm going to need a first derivative function drawn and the original function drawn. I'm going to draw the first derivative function on the left side, and I'm going to draw the original function on the right side, because that's the way the fundamental theorem of calculus is written. So, I'm going to come up with an example. My first derivative will be something, and my original function will be something as well. Let's say x squared plus x plus 1. I'm going to pick that for my original function. You guys tell me my derivative function. 2x plus 1. I want to graph both of these functions. I want to have a really good graph of each one so that I can compare points from this graph to this graph. All right? So I'm going to have to squeeze it down just a little bit and condense it because I really want some high values. So this is what I'm going to do. 2x plus 1. Here's my 1 for my y-intercept. And my slope is a 2, so I go up 2, right 1. What's that point?
1, 2.
1 comma 2?
1.
Let's try 3. Because I was already up 1. So if I'm going to go up 2, it's going to be 1, 3. What's the next point? What is it?
2, 5.
2, 5. From here, I'm going to go up 2, right 1. Name that point.
3, 7.
3, 7. Up 2, right 1. 4, 9. Somebody else? Come on, you guys. Up 2, right 1. 5, 11. Up 2, right 1. 6, comma 13. And so on, right? If you miss one of these points, you just go back and make it a little bit bigger. And down here, what's going to happen with the function? It's going to go where? Negative. It's going to go negative down here. All right, so this is my x-axis. This is my y-axis. And this is my function, which is my first derivative function, 2x plus 1. Now over here, I want to graph this. How do I graph y equals x squared plus x plus 1? 0, 1. Okay, I got you. 0, 1. Something else. 1, 3. Put a 1 in here. We come up with a 3. So 1, comma 3. Keep going. What's 2 squared? 4 plus 2. 6 plus 1. 7. What was my input? 2. My output is 7. So 2, 7. Go for a 3. 3, 13. So 3, that was a 7. 8, 9, 10, 11, 12, 13. 3, 13. Should we try a 4?
No.
Yes. 21? 4, 21. So 4, and that was a 13. 14, 15, 16, 17, 18, 19, 20, 21. 4, 21. Want to try 5?
No.
Me neither. Okay. So what about negative 1?
That would be 1. Wait, what? Negative 1.
Negative 1, 1? True. Okay, negative 1, 1. Which would tell you that your vertex has to be somewhere between there. Matter of fact, it has to be exactly in between there because your vertex falls on your axis of symmetry. Your vertex turns out to be the point 1/2, comma 3/4. And we'll just write V there and kind of point at it. Okay, that's my vertex, 1/2, comma 3/4. It's not going to play much of a role in what I have to do anyway. So your quadratic, this is your vertex, you're coming down, back up. Huh? Oh yeah, thank you. Negative 1/2, comma 3/4. And then over here it does the same thing, and I really don't care. So I'm just going to go ahead and draw my arrow up, because if I try to draw it, I'm not going to look symmetric. That y-axis is going to throw me off. I'm going to try to be symmetric over that y-axis, which I shouldn't. My axis of symmetry is x equals -1/2. So I'm just going to leave it like this. Okay, we're going to come back here. I need two x values on this graph that also coincide with x values on this graph, so I can use them as my a/b interval to make a comparison of the original function to its derivative. So what two values do you think I want to play with?
1, 2.
Here's 1, x equals 1, and
4.
you want to do 3, you want to do 4? I'll do 4. Here's 4.
What's the point?
Huh?
No.
There's 1 and there's 4. Here's 1 right here, and here's 4. This is what the fundamental theorem of calculus is going to mean. We're going to come over here and we're going to find the area of this, what's this shape?
It's a
Trapezoid. Okay, we're going to find the area of this trapezoid bounded by the first derivative function, the x-axis, x equals 1 and x equals 4. And we're going to do that using a trapezoidal rule. All right? So the area of a trapezoid is 1/2 the height times the sum of the bases. So we have a equals 1/2. I need to know the height of this trapezoid, and I need to know the sum of the bases. The bases of this trapezoid have to be the two edges that are what with each other? Parallel with each other. Those are the bases of the trapezoid. So actually they're the easiest thing for me to figure out. What's one base? How tall is this? 3. How tall is this? 9. So my bases are 3 plus 9. And now the height is the distance between those two bases. So what's the straight line distance between those two bases? 3. This gives me 1/2 of 3 times 12. So what's half of 12? 6 times 3? 18. So this area is 18. 18 squared units, if you will. We probably aren't going to use units of measurement very often when we first learn the fundamental theorem of calculus, but as we get on and we apply it into contextual problems, we definitely have units of measurement we have to pay attention to. Okay, so the area here is 18 squared units, and this is the area bounded by the first derivative graph, the x-axis, a equals 1, b equals 4. Now, I want you to look at 1 and 4 over in the original function, the antiderivative function of this graph. Look at x equals 1. Do you see its y-coordinate? Name it. 3. Look at x equals 4. Do you see the y-coordinate? Name it. 21. What is 21 minus 3?
18.
18. Does that not blow your mind or what? Okay, this is f of 4 minus f of 1. And this is the area, right? The area bounded by the first derivative function in the x-axis and x equals a and x equals b. Doesn't that just blow your mind that the integral, which is the summation of all of these little rectangles on the derivative function, represents the change in the height on the same interval for the original function? I think that just blows my mind. That fundamental theorem of calculus is just amazing. Okay. So, I want to put it in words a little bit. I'm going to erase what I have right now, just write it over here again. So the integral from a to b of a derivative function is equal to the original function evaluated at b minus the original function evaluated at a. How are we doing on time? Oh, 9 minutes. 9 minutes? Okay, we're still good. All right. So this thing right here, this whole concept, is what we did when we found this area. So this concept represents the area bounded by f prime of x. What else? bounded by, I've said it 2 or 3 times already, the derivative function,
The x-axis.
the x-axis,
X equals 1 and x equals 4.
x equals a and x equals b. That means that we have the interval from a to b. That's all it's saying. This is my a, this is my b, and this is my interval from a to b. You know how a lot of theorems and rules that we talk about, they start off with a function being continuous on the closed interval a, b, differentiable on the open interval a, b. This also has the interval a, b involved in it, okay? All right, so the area bounded by the first derivative graph, or any derivative, the x-axis, x equals a and x equals b, is equal to that takes care of my equal sign. What's this mean?
The difference in the height of the 2 endpoints.
The difference in the heights, okay, of the 2 endpoints on the interval. I would take that, of the original function on the interval. Okay? I want you to get used to saying the word change in, or the phrase change in. So it's equal to the change in, even though the difference works, okay? Minus does mean difference, true, but it also represents the change. I'm going to put the phrase, that change together. The change in the, and I'm going to put y coordinates, or the heights, or the change in height on the original function. I can just say f of x because I've already said that's f prime x.
Yep.
Okay? So it's the change in the height on f of x on the interval from a to b. You can word this a ton of different ways, but that's what's going on. What time we have? 12 minutes? Okay, we're doing good. All right. I like to reword this function, this theorem. I like the Fundamental Theorem of Calculus this way, but I also like it another way. So I'm going to erase what I have written right here. Do you have this down in your notes someplace? So I'm going to erase this, and I'm going to manipulate the theorem and the way it's written, and then I'm going to reword it. But it's going to be the same concept, just warped a little bit. I'm going to add f of a to both sides of the equation. Am I allowed to do that? Mathematically? I can add the same quantity to both sides of an equal sign, I still get equal quantities. And now it's going to say f of a plus the integral from a to b of f prime of x dx is equal to f of b. Now let's look at our picture and see if this makes sense. F of a was 1. So what was f of a? With a was 1. F of 1, what's that? 3. So 3 plus that area, which is 18, equals f of b, 21. This height right here is f of b. This height right here is f of a. So if you take f of a, you add this area to it, don't you get f of b?
Yes.
Okay. So in my world, I say start plus change equals n. Start plus change equals n. And this also is the Fundamental Theorem of Calculus, reworded. So I'm going to pause there.